learned about stoichiometry, stoics. So stoichiometry, in case you've forgotten, is just looking at the ratio of the different components in our balanced chemical equation. So if we put in 2 of these C8H18s, that's octane, and we have enough of everything else, then we'll get out 18 H2O. And this works for molecules, or our smallest little ittiest bittiest units. It also works if we scale it up to moles, since we're scaling everything up at the same rate. So moles being, again, like our dozen. So usually I'm thinking of these in moles. We can also do them just without the moles. You can leave that out of your balanced equation. A lot of the calculations that we're going to be doing in this class for the near future are going to be these mass-to-mass problems. We're going to be doing these quite a bit, so I'll get pretty good at finding molar mass. Sometimes I'll give you those on the exam to save you time and brain power. We're also going to be adding on new ways that we can swap out some of these early and late steps to make the problems a little bit more interesting for things like gases and solutions and other things that are like that. But for now, it's mass-to-mass stoichiometry. Another example is that ammonium nitrate decomposes to dinitrogen monoxide and water according to the following equation. In a certain experiment, 45.7 grams of ammonium nitrate, that's the NH4NO3, is decomposed. Find the mass of each of the products formed. So we're looking for the mass of each. So we've got 2 answers that we'll be expecting to give. Fortunately for us, this chemical equation is balanced. Our clue that it's balanced is that we've got a 2 in front of our H2O. So we've got coefficients put in. I would guess that almost never you're going to see an unbalanced equation that also has coefficients in there. Usually it'll have no coefficients, meaning it's potentially not balanced, or it will have coefficients, meaning it is balanced. So we'll do basically 2 mass-to-mass calculations, but they're going to have the same front end. So our steps, we'll write it up here along the top. We're starting with grams ammonium nitrate. We can go from grams of ammonium nitrate to moles of the same. And then we've got 2 options. We're going to take both of them. Just which one do we take first? We're going to convert to moles of N2O. And in a second situation, we're going to convert to moles of H2O. And then we'll take each of those to grams of the respective chemical, since we were asked to find the grams of each of our products. So that's our solution map. We need a couple of things. 5 things we need for our solution map for each of the steps. We need our molar mass to complete this first step. We also need a molar mass for these last steps. And then the last 2 things that we need are ratios, as I often call them. That's our stoichiometric ratio. So looking at the coefficients in our balanced equation for each of our products with our one reactant. So I'm going to start off by calculating molar mass just to get that out of the way. So for ammonium nitrate, we've got 2 nitrogens. We've got 4 hydrogens, we've got 3 oxygens. So we've got a molar mass of 80, write it down here, 80.043. Water is 18.015, and N2O is 44.013. These are all with units of grams per mole. Any questions so far on the process? Kind of all just been set up. We'll write out some numbers and the calculations next. All right, so starting with our 45.7 grams of ammonium nitrate, we need to convert that to moles of ammonium nitrate, so we're going to divide by our molar mass. That puts the grams on the bottom, and since the moles were on the bottom already, they flip to the top. So our units of grams cancel out, and we're left with moles of ammonium nitrate. We're going to need this number for both of our calculations, for our products, for our N2O and for our H2O. So I'm just going to copy paste that down below. Sorry for scooting the screen. And we'll do the N2O calculation on top and the H2O calculation below. So now that we've got converted into moles, we need to convert our chemical. So converting ammonium nitrate to N2O, our coefficients are 1 and 1. So on the top, we'll put 1 N2O. You could think of that, or write in 1 mole N2O as well. That's also accurate. And on the bottom, 1 ammonium nitrate. So we've now converted our ammonium nitrate out, and we're talking about the amount of N2O that we would be producing in moles. And the last step is to use our molar mass for N2O to convert back to grams. So the whole calculation would look something like that, with units of grams N2O. Any questions at all about that? Yes.
For the 18.015 for the molar mass of H2O, would you multiply that by 2 because of the 2 coefficient, or is it just the molar mass of H2O itself?
We'll have a separate step for doing that, using that 2. That's the stoichiometry step. Okay, so our grams is 25.1 grams after we round for 3 significant figures. All right, looking at our H2O section, that's down below. Our ratio is going to be 2 H2O to 1 NH4NO3, ammonium nitrate. So we put 2 H2O up top, 1 NH4NO3 below that. So this is again converting our chemical unit from ammonium nitrate into H2O. Now that we've got moles of H2O as our units, we can multiply by our molar mass of water, to get back to grams. And our mass of water is 20.6 grams. Any questions about either of those? Basically got 2 for 1, but we only had to do 50% more work. All right, next up, getting back to bacon, back to our BLTs. There's a concept called limiting reactant, meaning something that we'll run out of that kind of limits the amount that we can make. In the case of this example with BLTs, bacon, lettuce, tomato sandwiches, we've got our balanced equation, our recipe for making BLTs. Let's say we root around in the fridge. We find that we've got 12 strips of bacon, 5 pieces of lettuce, 8 slices of tomato, 8 slices of bread. How many BLTs can we make strictly following this recipe? Of course, if this was us at home, we could probably finagle something, make some Franken BLTs that are not quite according to recipe. So the way that we would figure this out, right, we've got a bunch of different ingredients. We've got different amounts of each of those that we need to make. So we want to see what's the fewest number of BLTs that we can make. So we're basically going to be doing 4 stoichiometry steps here. So we've got bacon. We've got our lettuce, we've got our tomato, and we've got our bread. And we'll convert all of these to BLTs. So assuming that we have enough of everything, how many BLTs can we make with that one ingredient? So for our bacon, 12 bacon, our ratio is 1 BLT out for 4 strips of bacon in. So 1 BLT per 4 bacon. And we could make 3 BLTs, given the amount of bacon that we have. Let's check for lettuce. For our lettuce, it's 1 piece of lettuce for 1 BLT. Hopefully pretty straightforward in terms of the math. I'm writing it out just to show you, in case you needed it. So 5 lettuce means potentially 5 BLTs. We've also got tomato. Let's see how many BLTs we can make with our tomatoes. 8 tomato. Our ratio is 2 tomato in, 1 BLT out. So we would be able to make 4 BLTs, given the amount of tomato that we have. And then our last ingredient is the bread. 2 bread in, 1 BLT out. That's our conversion, our ratio. So 8 bread divided by not 4, but 2. We need 2 slices of bread to make a sandwich. And that sandwich is a BLT. So we could make 4 BLTs. which of these is the actual number of BLTs that we can make? The actual number of BLTs that we can make is 3. So for each of these calculations, we're ignoring all of the other reactants, all of our other ingredients. We're just saying, all right, well, if we have enough of everything else, how many can we make? But this 3 BLTs that we get out for our bacon means we're going to run out of bacon on our 3rd BLT. We would not have enough bacon to make a 4th BLT, even though we've got enough bread and we've got enough tomato. And we definitely can't make 5 BLTs because we would run out of bacon, tomato, and bread. So the smallest number is the actual amount that we can make. Another way that we could have done this is if you just take each of these numbers and divide by the coefficient on it, that would give you kind of the number of batches, as I would call it. So like if we had a number in front of our BLTs that wasn't 1, if we had like a 3 or a 5 in front of our BLTs, the math becomes a little bit less easy to do going all the way to BLTs. But we could look at batches of ingredients. So just dividing by 4 and not worrying about multiplying by 1. If that makes sense to you, you're welcome to do it for limiting reactant stuff, but you don't have to. So if this were a chemical reaction, our bacon is going to be our limiting reactant. It runs out first and limits the amount we can make. And then 3 BLTs would be what we call our theoretical yield. The theoretical yield is the amount we can make if everything goes perfectly. And you may know that things often don't go perfectly, so we will typically not achieve our theoretical yield. In the world of making sandwiches, it's a lot easier to hit your theoretical yield. In the world of chemicals, like an excellent result would be 90% of your theoretical yield. And some results might be more like 10 or 15%. Any questions about our limiting reactant or our limiting ingredient and our theoretical yield? All right, let's say that we are putting together our BLTs. We're working on them in the kitchen. We're taking them out, setting them out on the sideboard next to the kitchen table. And as we're working on our second sandwich, our dog decides that he also wants a BLT and jumps up and steals one of those BLTs off the countertop. Obviously, our dog is getting a scolding and maybe going into his kennel. But we are also sad because we had enough bacon for 3 BLTs and now we only have 2 BLTs. And so the 2 BLTs would be the actual yield. That's the amount that was actually produced. And this typically differs from the theoretical yield. In a perfect world, our dog doesn't steal our BLT, and we get to eat 3 BLTs or share with friends. We will be using actual yield, theoretical yield, and limiting reactant in lab. Question?
So would the theoretical yield be like the predicted amount?
Yeah, the theoretical yield is the predicted amount. We expected to make 3 BLTs.
Dog ate it.
Dog ate one. Should have put them further back on the countertop, I guess. And from our actual yield and our theoretical yield, we can calculate our percent yield. So our percent yield is our actual yield, how many sandwiches we produce, divided by our theoretical yield, how many sandwiches we could have or should have produced if everything went perfectly. And then we multiply by 100%. With the analogy of making sandwiches, calculating a theoretical yield feels a little bit silly. If we were a big business, if we were working at a Chipotle and we were a manager, then theoretical yield might make a little bit, or sorry, percent yield might make a little bit more sense. We're going to have some loss. We're going to have some ingredients that need to be thrown out. So having some idea of how much we have to over order would make sense. If you're having a large get-together and you occasionally burn your bacon, or my old example was pancakes. Occasionally the pancakes go bad. You drop a pancake. It's important to know, right, that you're probably going to need a couple extra sandwiches. You're going to need a couple extra pancakes so that everyone can get fed. Something might happen. Might be a bad piece of lettuce. Who knows? In the chemical world, the reason that we would calculate percent yield is that usually our chemical reactions are only moderately successful in terms of what we would probably think of. So like a 50% yield would probably be pretty good in many circumstances. If we're expecting, or if we need to make a certain amount, like in the case of BLTs, if we need to make 15 BLTs, but only 67% of them turn out right, we're not going to buy ingredients to make the amount that we're trying to hit. We're going to buy extra ingredients because we know we're going to lose some, because we're snacking, because our dog steals some, because we burn the bacon, etc. So that's kind of how we would use this in a real-world lab scenario. The actual yield is always going to be determined, or in the case of like on an exam, given to you. You can't calculate an actual yield. And that's going to depend on your reaction conditions. In the case of the BLTs, if our dog's outside, we get a better yield of BLTs, right? He can't come in and steal off the countertop. In the real world, our actual yield is almost always less than 100%. It can be above 100%. If it's above 100%, right, we're not magically like doing alchemy. We've like created new things out of nothing. It's usually because of some error that we made. So it can be over 100% because of experimental error. We got a little bit of dirt in our product. We didn't dry it out all the way, so there was some water that was still in there. We forgot to put our little piece of whey paper on the scale and press tare before we put our product on. Lots of things like that. So our measurements, we probably made some errors if we got a yield over 100%. Typically, it's going to be below 100%. Some of the product doesn't form, or product is lost in the process of recovering it. We left some in the beaker. Some of it spilled off of our little whey paper. We wanted to know what it tasted like. You know, lots of things that could stop you from getting your 100% yield. So a summary of some of those ideas. Your limiting reactant or limiting reagent is the one that is completely consumed, all used up, and runs out first. It's also the reactant that makes the least amount of product. So like with our BLTs, that was 3. Everything else we could make more of. our theoretical yield, as one of you put it, the predicted yield. The amount we were expecting without any errors. And then our actual yield is what we actually got. It's the real amount. And our percent yield uses this formula, actual yield over theoretical yield times 100%. Any questions? All right, that'll wrap up this chapter.